Hello everyone, let's continue explaining asymptotic notations. In the previous video we learned that analyzing the performance of an algorithm should be machine independent, so we need to use asymptotic notations. By using asymptotic notation, we drop lower order terms and ignore leading constants. So if I take the following example, I'm more interested to look at the n cube only. And we use certain terms for time, such as the following functions that are sorted from the slowest to the fastest functions in regards to the increment of their output when increasing the value of n. So we have a representation for all constants, and here we mean that any constant value will be represented by 1. We have the logarithmic function, root, linear, quadratic, cubic, exponential, and so on. Let's prove this to make you understand it. If we just take a value of n equals 1, we can see that log n is less than n squared, which is less than the exponential function. Now we increase n and see how other functions are increasing. For n equals 4 and 8, so we can see that the exponential function has the fastest increment here when we increase the value of n. Now let's see the types of asymptotic notations that we can use to represent the time complexity. The big O notation. This works as an upper bound of a function. The definition says that the function fn equals O of gn if there exist positive constants c and n0 such that fn is less equal to c into gn for all n greater than n0. Now let's understand what this means by looking at the following example. If I have the function fn equals 6n plus 1, then 6n plus 1 should be less than something I should write here, such that it's greater or equal to 6n plus 1. So I can write anything that should be greater or equal to this one. And here I should write only one term and drop low-order terms and constants. So I will take that high-order single term and add another coefficient c to it to make it greater or equals to 6n plus 1. So I can write 10n. If I take 1 as a value of n, this will be 7, and this will be 10. And 10 is greater than 7, so this is for all n greater or equal to 1. Now this is fn and this is c and gn. So this is true, and fn is O of n. Now when the upper bound is n, then also all upper terms are true. So we can also write 6n plus 1 less equal to 10n squared. And fn equals O of n squared. This is also true. But low-order terms are not true for this case, as those are the lower bound here. So the root n or log n are not true. Now big omega notation. This works as a lower bound of a function. The definition says the function fn equals omega of gn if there exist positive constants c and n0 such that fn is greater or equal to c into gn for all n greater than n0. Is very similar to the big O notation, but only the symbol is different, and here it's greater or equal to c into gn. Now if we take this example, if I have the function fn equals 6n plus 1, then I can write 6n plus 1 greater than just 1 into n for all n greater or equals to 1. This is c and this is gn, so this is true, and fn equals omega n. Now when the lower bound is n, then also all lower terms are true. So we can also write 6n plus 1 greater or equals to 1 log n. And fn equals omega of log n. This is also true. But upper bound terms are not true for this case. The last one is the big theta notation, and this works as an average bound of a function. The definition says that the function fn equals theta of g of n if there exist positive constants c1, c2, and n0 such that c1 into gn is less equal to fn and that is less equal to c2 into g of n for all n greater than n0. Now, if we take the same example, we already found the lower bound and the upper bound, so we can write this directly. This is C1, Gn, C2, and Gn, so this is true and Fn equals theta of n. This is the average bound of a function, and this is exactly equal to n. So I can't use n squared and say that Fn equals theta of n squared, so this is wrong. It's always recommended to use the theta if you know the exact value, but if you are not able to do that, you can use the big O and omega notations. Asymptotic notations have some properties, so let's check them out. The first one is reflexivity. We have the definition here. If we have Fn given, then it's O of Fn. Let's take an example. If Fn equals n cubed, then it's O of n cubed. So a function is the upper bound of itself. Since the upper bound is any function that is greater than or equal to, and this is similar to the lower bound, where any bound that is lower than or equal to is a lower bound function. Second property is the symmetry. If Fn is theta of Gn, then Gn is theta of Fn. This property is only valid for theta notation. As an example, if we have Fn, then Gn is theta of Gn, which is n squared, and Gn equals theta of n squared, that is Fn. So when both functions are the same, then they are symmetric. So one of them is the theta of the other, and the other is the theta of the first one. Now, transitivity. The definition says if Fn is O of Gn and Gn is O of Hn, then Fn is O of Hn. Let's take an example. If we suppose Fn equals n and Gn equals n squared and Hn equals n cubed, then n is O of n squared and n squared is O of n cubed, then n is O of n cubed. You see that Fn is n, and this is O of n squared, which is also g of n. And this in turn is O of n cubed. So n is O of n cubed. We see that Gn is the upper bound of Fn, and Hn is the upper bound of Gn. Then Hn is the upper bound of Fn as well. The last one is transpose symmetric. This is true for big O and omega notations. The definition says if Fn equals O of Gn, then Gn is omega of Fn. As an example, if Fn equals n and Gn equals n squared, then n is O of n squared, and n squared is theta of n. So for n, n squared is the upper bound, and for n squared, n is the lower bound. So one function is the upper bound of the other, and the second one is the lower bound of the first one. Thank you so much for watching, and please subscribe if this helped you.